Hello, everyone. Right. Hello. Hello, everyone. Excellent. Good to see you all. So let's do some maths. So apologies, I wasn't able to do the webinar last week. Try to rectify, if that's the word. Okay, so we're talking about, oh, apologies. We're not talking about inequalities. We are talking about we're talking about logs and exponents, of course. Mm-hmm. Just a second. Tutorials. Tutorials, you need to talk to your tutor. Yes, your tutor has an individual's timetable, so it's up to them. So yeah, you should be receiving 3 tutorials for each assignment. Okay, if that's not happening, do let us know. Let me know. Well, we'll see what's going on. Right, so we talking about exponents and logs, and at the end I've prepared a question on electricity, so hopefully we'll get to there. We'll get to the electricity question. But let's start with exponents and logs. So this is an exponential equation. I'll be doing equations mostly, but I'll be using the properties of exponents and logs effectively. So you have root 5 times 0.2 to the power 1 over 2x minus 0.04 to the power 1 minus x. Okay. So what can I do here? And any advice that you would give me? Oh, yes, very good. Get everything as a power of 5, of course. So square root of 5 is 5 to the power 0.5. 0.2 is 5 to the power minus 1. Hence, 0.2 to the power 1 over 2x is 5 to the power minus 1 over 2x. 0.04 is 1 over 25, which is 5 to the power minus 2. Therefore, 0.04 to the power 1 minus x is 5 to the power minus 2 plus 2x. And we can write that down. So 5 to the power 0.5 times 5 to the power minus 1 over 2x. Well, you can say equal 5 to the power minus 2 plus 2x. Combining the two 5s, so it's 5 to the power 1/2 minus 1/2 1 over 2x equals 5 to the power minus 2 plus 2x. And one of the properties, one of the very important properties of an exponential function, an exponential function is a one-to-one function. It's a monotonic function. So a to the power x is a monotonic function. What does that mean? Well, it means it's either constantly increases or constantly decreases. So if its a is less than 1, it is constantly decreasing, and if a is greater than 1, it's constantly increasing. So this is a monotonic increasing and monotonic decreasing. And monotonic functions are also one-to-one functions. Monotonic functions are one-to-one. All monotonic functions are one-to-one functions. So monotonic functions. Is there anyone here who doesn't understand what a monotonic function is? Don't be shy. It's not something you study in A level. Just please let me know. Otherwise, do you know what a... Okay, the question, do you know what a monotonic function is? Yes or no? Just simply that. 1, 2, 3, 4, 5, 6, 7. There's 7 of you. I've got so 2 people haven't replied. If you haven't replied, can you reply, please? Okay, good. All right, so I don't need to go through. So a moment one-to-one functions, and that means if this is x1 and this is x2, right? F of x1 and f of x2 are always different numbers, so it's a one-to-one function. So for monotonic function or monotonic functions, if f of A equals f of B, then A equals B. It's not always the case. For example, if it doesn't work for non-monotonic function. Example. 3 to the power x, f of x, is a monotonic function. So if 3 to the power a equals 3 to the power b, then a equals b. It has to. 2. F of x equals x squared. Well, let's do another simpler example. Sine x is not a monotonic function. So that means sine a, if sine a equals sine b, then this does not mean sine b. This does not mean a equals b. Okay. Do you understand what I'm talking about? On a scale of 0 to 10, please. Oh, lovely. Lovely. Lots of 10s. Excellent. So for because 5 to the power x is a monotonic function, therefore if 5 to the power that is equal to 5 to the power that, then necessarily 1/2 minus 1 over 2x has to equal minus 2 plus 2x. And then we just need to remember that x is not 0 because 1 over 0, you're not allowed to have x equals 0. So let's see what we get. We multiply everything by 2x. So that's going to be x minus 1 equals minus 4x plus 4x squared. 4x squared minus 5x plus 1 equals 0. This is special case. This is a special case number 1. You see that the sum of coefficients is 0. 4 minus 5 plus 1 is 0. So it's a special case. That means x1 is 1. x2 is c over a, which is 1 over 4. So answer 1 and a quarter. So right. Second one. Well, here we just need to combine like terms. So like terms, this one and this one, this one and this one. So we got 35, well, 35 minus 1, 3x squared plus minus 35 plus 1, 5 to the power 2x equals 0. So what can we do here? Well, this is 36. 36 multiplied by 3x squared plus or minus what? 36, no, sorry, 34, of course. You didn't see that. 3x squared minus 34, 5 to the power 2x equals 0. 34 is a common factor. 34, 3x squared minus 5 to x equals 0. That means 3 to the power x squared minus 5 to x equals 0. All right, 3 to the power x squared equals 5 to the power 2x. Well, there are different things we can do here. Well, not too different. You can just take, if you have powers with different, so this is different from the previous one, because in the previous one you had you had 5 and 5. Here you have 3 and 5. What you can do here, you can take logs of both sides. Take log of both sides. Have you studied logs yet? Have you studied logs at school? Yes or no? Okay, so this should be easy for you. So you take log 3x squared equals log 5 to x. Then there's a property of logs. So log x to the power p can be written as p log x. So x squared log 3 equals 2x log 5. And now you take everything to the left. It's going to be x squared log 3 minus 2x log 5. Oh, before writing this, what is the temptation here? What is the first thing that comes into your mind here that you shouldn't do, but yeah, to cancel s, but cancel x, but don't do that because it can be 0. And if you look, there's no objection of x being 0. There's no limitation on x. Well done. Okay. So now you can take x out of the, x is a common factor. So x, you have x log 3 minus 2 log 5 equals 0. So either x equals 0 or x log 3 minus 2 log 5 equals 0. That means x is 2 log 5 over log 3. You can simplify that as 2 log 5 base 3. That's the answer. So 2. to answer. X equals 0. X2 is 2 log 3, 5. Log 5 base 3. Okay, things are getting serious. What should we do here? Oh, how did I go log in base 3? Well, there's a formula, the change of base formula. Change of base formula. And it states that log BA, so any log can be written as a log in any base. You can change the base to whatever you like. Log CB over log CA. C is anything. Of course, there are limitations. C is greater than 0 and C is not equal to 1, because then otherwise that wouldn't make sense. So log 3, 5 can be written as, for example, ln 5 divided by ln 3, or it can be written as log 5 divided by log 3. And the opposite is also true. Log 5 over log 3 can be written as log 5 base 3. Does that make sense, Carrie? Okay, happy to help. What can we do here? Any ideas? No, 2 is a standalone number. Write logs as power of 2. That would work. That would work, except that would make things way more complicated. For example, if we write this as a log base 2, so it's going to be log base 2, 1 over square root of 1 plus x. That's going to make things harder. So get all the logs the same base, yes. The question is, which base? Not just logs, but everything that is not a log as well. Get all logs to base. Zero 0.5. You could do 0.5. Yeah, I don't see why not. Although I'm just going to say a quarter, base a quarter. I think 0.5 would work, but if we take it to a quarter, that's even better. Let's see how it is better. So what can you do here? Well, you can to base a quarter. There are two ways doing it: the clever way and the brute force way. Let's try to do it the clever way first. Oh, it's clever-ish. It's particularly clever. So log 0.5 square root 1 plus x. And, well, it could be written as log 0.25 to the power 1/2. No, that doesn't make sense. 0.5. Oh yeah, to the power 1/2. So a quarter. Quarter to the power a half. Because 0. Quarter to the power half is 0.5, yes. And this is 1 plus x square root. Now there's a rule. I hope you know this rule. So log AQ xp can be written as P over Q log AX. So if the base of a log is to a power, this power can be brought to the front as the denominator. Let's just for simplicity make it like this. If you have a to the power q, you can write it as 1 over q log a. Therefore, this is 1 over 1/2 log a quarter square root of 1 plus x. And 1 over 1/2 is 2 log a quarter square root 1 plus x. And the 2 is brought as a power, so it's log a quarter 1 minus plus x. So you see, it gets easier. All right, 3 log a quarter 1 minus x can be written as log a quarter 1 minus x cubed. That's the easy one. All right, getting to the advanced one, log 1/16 of 1 minus x squared equals. So we're taking this term. All right, so we're using the same principle. So log 1 quarter to the power 2, 1 minus x squared, 2. This is going to be log 1/2 log a quarter 1 minus x squared, 2. And this half is brought as a power. So log 1 quarter square root of 1 minus x squared squared. That's equal to log 1 quarter 1 minus x squared. Usually square roots, that's the sticking out bit that you want to get rid of as soon as you can. Fractional powers, So that's a question. Is there anything that sticks out that hints which base you should use? Yeah, trying to get rid of square roots, I'd say it's a usual stuff. Can you show how to derive that rule? Let me think about it. I'll think about it. I don't remember how to derive it. I've made a deliberate mistake in the last step. I've made a mistake here. Can somebody tell me what is the mistake? Jed, you're correct. You need the absolute value because square root of x squared is not x, it's modulus x. That's very important. Minus? What do you mean? What do you mean minus? This is a question. Should you not include the minus as well? What do you mean by minus? I'm not sure what you mean. Square root is square root of x is always non-negative by definition. Definition. Minus x. Right. Why is square root of x the modulus of x? Well, simply because it has the same properties. Like if you take minus 3 squared, it's going to be 3, not minus 3. Then when should you include the plus minus, and when do you just have the absolute value? Look, I think you're confusing stuff. If you have x squared equals, I don't know, 7, you're saying, what can x be? Well, x could either be root 7 or it could be minus root 7. But the root 7 is still positive. The root is always positive. So when if you're writing the square root of x squared is equal to x, for example, well, that does not true because if x is negative, for example, it doesn't work for negative x. Doesn't work for x less than 0 because square root cannot be negative. Square root is always greater or equal 0. Is that making sense, or is it still confused.com? Okay. Okay. So what I've missed here is I've missed the modulus. So it has to be modulus. Okay. Now, working with the modulus is is a pain. You probably know that. So let's see if we can make our life easier. Let's see what can x be? Well, if you look here, you have the square root of 1 plus x. You're not allowed to take the square root of negative numbers. So that means 1 plus x must be positive. That means x is greater than minus 1. Now looking at this bit, you cannot take a log of a negative number. Yes, log is only defined for positive numbers. So that means 1 minus x has to be positive. And that means x has to be less than 1. Interesting. So overall, x can only take values between minus 1 and 1. And if x is between minus 1 and 1, what does that tell you about 1 minus x squared? It is positive, because if x is between minus 1 and 1, that means 1 minus x squared is always positive. And that means we can now remove the modulus sign symbol, as 1 minus x squared is always positive. Then the modulus of a positive number, the modulus of x, is equal to x if x is positive. So it's simply log a quarter 1 minus x squared. So I made such a faff about adding the modulus, and now I've found a reason to remove it. But why am I removing it? Because I know what a pain it is to do modulus. And finally, the 2. The 2 can be written as a log. And let's do it the following way. I'm going to write 2 as no. Sorry, it's fine. I'll just write it as a log. It's going to be log a quarter 1/16. I believe that this is correct. 1/16. Yeah. All right. And now we come back to the equation. So we have log quarter 1 plus x plus log a quarter 1 minus x cubed equals log a quarter 1 minus x squared plus log a quarter 1/16. Now, if you're adding logs, we are multiplying them together. So this is a log a quarter 1 plus x 1 minus x cubed equals log a quarter 1 minus x squared over 16. And because log is a one-to-one function as well, log is a monotonic function. So if log a equals log b, then a equals b, because log is a monotonic. Log is monotonic. And that means 1 plus x, 1 minus x cubed equals 1 minus x squared over 16. Well, I'll take 16 over here. The last thing I want to do is open the brackets. So I'm going to factorize instead. 1 plus x, 1 minus x cubed. No, I can't really factorize it. I can factorize this bit. 1 minus x, 1 plus x. So putting everything to one side. So, and finding the common factor. The common factor is 1 plus x, 1 minus x. So it's 1 plus x, 1 minus x, open bracket, 16, 1 minus x squared minus 1 equals 0. And that means that 1 plus, so from here, that means 1 plus x is 0, or 1 minus x is 0, or 16, 1 minus x squared minus 1 is 0. So because this is a multiplication of three things, so x equals minus 1. Is it a valid answer? No, it is not, because we've established, remember, that we've established that x is between 1 and minus 1, not inclusive. Therefore, not valid. That x equals 1 is not valid. And here we have 16, 1 minus x squared equals 1. 1 minus x squared equals 1/16. 1 minus x equals plus or minus a quarter. X is equal to 1 plus minus a quarter. So x equals 5/4, or x equals 3/4. All right, which one of them is valid? Which one is not? Yeah, not valid. And this is the only valid answer. So answer. All right. So stepped on my toes a little bit here. Log in base 1/4 of 1/16. So what is the question? Log 1/4, 1/16. Yeah, oh, it's 2. Oh, you are helping me. Okay, sorry. I didn't understand the question. Okay. X to the power log x plus 5/3 equals 10 log x plus 1. Okay, well, this is 2 powers, so we have like a to the power something equals b to the power something. What you do in this case, you just take logs of both sides. And how can you know that you can? Well, first of all, you see log x. That automatically means that x is positive. So that means x is a positive base. Therefore, you have this is a positive number. This is a positive number. You're taking log of both sides. and a log of a positive number exists. Both sides are positive. Take log base 10 of both sides. Yes, LG means log base 10. So LGX is the same as log x, and it's the same as log base 10x. So it's different notations. You will see those. You will see different notations in different books. So you have log x to the power log x plus 5 over 3 equals log 10 log x plus 1. So you can put this in front. It's going to be log x plus 5 over 3 multiplied by log x equals log x plus 1 multiplied by log 10. Well, we know that log 10 is 1. That makes life easier. So we have log x plus 5 over 3 multiplied by log x equals log x plus 1. Multiply the whole thing by 3. So it's log x plus 5 log x equals 3 log x plus 1. Let's open the brackets. So log squared x plus 5 log x minus 3 log x minus 1 equals 0. So log squared x plus 2 log x minus 1 okay. I don't particularly like that. Can we solve that? Oh yes. Yes, that's 3, of course. Yeah, that makes more sense. All right. Yes, it's a quadratic equation, and it's a special case. So log x is either equal to 1 or log x is equal to, so it's a special case. Or log x equals minus 3. And from here, well, x1 is 10 because log 10 is 1. And x2, so which number to the power minus 3? 10 to the power minus 3 is 0.001. Is x plus 1? No, it's not part of the log. It would be x plus 1 like this. It's log x plus 1. Yeah, that's might be that's why, because that's why I was confused. Okay. Now we talk about differential equations. This is a differential equation. It doesn't look like the differential equation that you might be used to. but it certainly is one. How do we know it's differential equation? Well, it contains differentials, the dv and dm. Where does this come from? Okay, well, what is this? Is not the Tsiolkovsky equation, but it is a rocket equation. It is a rocket equation. I don't remember whose equation, who invented this equation, but anyways, what does this mean? You have a rocket of mass m in deep space, so there's no gravity or anything, no external forces, and it expels some gas of mass dm with velocity u. U is the velocity of the gas, and that causes a small change in the speed of the rocket dv. And the conservation of momentum says that udm must equal to mdv. Well, why minus? Well, because dm is the mass of the gas, but it's also the decrease. dm is the decrease in mass of the rocket. So we use a minus here. So dm is negative. That's why we have to put a minus to compensate for the negative. No, it's not because it's in the opposite direction. Well, I mean, it is in the opposite direction, but this would be mdv minus udm, because it's in the opposite direction. Udm is equal to 0, and that would lead to mdv equals udm. So if you we've already considered that it's in the opposite direction, but now you consider that dm is negative because it's a decrease in mass of the rocket, so you put a minus here. That's not that important. Important is that we have an equation. We have an equation which is a differential equation of a rocket differential equation. It's incredibly simple if you think about it. And Tsiolkovsky solved this equation and came up with the Tsiolkovsky rocket equation. Okay, so let's have a look. So just to remind you, m is the mass of rocket. And dv is the increase in speed of rocket. U is the speed of expelled gases. And dm is the change in mass of rocket. But the rocket changes mass because it loses gas, loses fuel. So it's the mass of expelled gas. Because that's the change in the mass of the rocket, and the mass of the expelled gas is the same thing, except one is positive, one is negative. We take the negative for the gas. Okay. Now, from the conservation of momentum, we obtain this equation. Okay, let's write it down. Let's solve it. mdv equals minus u dm. So u is a constant. M is not a constant. So we take m over here. So dv equals minus u dm over m. And now we integrate it. We integrate both sides. And for the limits of integration, we put the initial and final values for the variable after d. So this is dv. We're integrating with respect to velocity. That means we take the initial velocity and final velocity. The initial velocity is 0. The final velocity, well, let's call it v0. For the mass, we initial mass, let's call it v final, and the final mass. Okay, initial mass and final mass. Now the integral of dv. What's the integral of dv? Very well, thank you. So it's v between limits of 0 and vf equals minus u. What's the integral of dm over m? Thank you. Logarithm of m between limits mi and mf. So this is vf minus 0 equals minus u logarithm m final minus logarithm mass initial. So the final velocity is the minus the initial velocity multiplied by logarithm the final mass divided by the initial mass. How does it make sense that it's negative? Well, if you look, the final mass is always smaller than the initial mass. So this logarithm will always be negative. So we can rewrite it as, well, we can take the power. This is power, but this is minus 1. We can take minus 1 as a power here. We can take it as a power here. It's going to be u logarithm the initial mass divided by the final mass. And that's brilliant. That's a brilliantly simple equation. The final velocity of a rocket is the initial velocity, is the speed of the gases multiplied by the logarithm of the initial mass divided by the final mass. This is called the Tsiolkovsky rocket equation. So when they say it's not rocket science, you say, well, of course it's not rocket science, because rocket science is actually not very difficult. It's a simple equation. So let's say you have a rocket of 1,000 kilograms and the speed of the gases is 2,000 meters a second. How much fuel do you need to reach orbital velocity? That means to take it to space. That's the minimum speed to take it to space. Well, you can work it out. Vf is equal to u logarithm initial over final. You can, it's Vf over u equals logarithm m initial over m final. Then you exponentiate both sides. That means if a equals b, then e to the power a equals e to the power b. You're allowed to do that. So e to the power vf over u equals e to the power ln mi over mf. And you also know that e to the power ln a is a. That's the main logarithmic identity. So that is equal to mi over mf. So therefore we have mi initial mass divided by mf is equal to e to the power vf over u. So the initial mass of the rocket is the mass of the final mass of the rocket multiplied by e vf over u. So the initial mass of the rocket is, well, the initial mass of the rocket is the final mass plus mass of fuel. Right? That makes sense. I hope that makes sense. But okay, the initial mass of the rocket is going to be the final mass. The final is the dry mass. Dry mass is 1,000 kilograms. 1,000 multiplied by e to the power 8 kilometers a second. 8 kilometers a second over 2,000. So 1,000 multiplied by e to the power 4, which is 1,000 multiplied by e. Where is e? E to the power of 4. That's 54,598 kilograms. That's the starting mass of the rocket. And of course, the mass of fuel that is needed is 53,600 kilograms. Mass of fuel needed. So to take 1 kilogram to space, or so to take 1 kilogram of space, you need 53 kilograms of fuel. That's why the rockets are so big, right? Because most of the rocket is fuel. What if you want to travel at the 10th of the speed of light? Well, the initial mass of the rocket is going to be 1,000. Why am I saying 1,000? Oh yes, 1,000 multiplied by e to the power 1/10 of the speed of light, which is 30 million kilometers a second. So 30 million meters a second divided by 2,000. So that's 30,000, 15,000. That's 1,000 e 15,000. I can't imagine how big this number is. And my calculator will not calculate that. Let's see if I can do this calculator. Calculator. So it's 1,000 multiplied by e to the power 15,000. Thank you, Google. I don't think this one. Okay. Benefits calculator. No, okay. Basic. No, that's definitely won't do the trick. Can anyone calculate it? Does anyone have a good enough calculator to do that? It's 1,000 e to the power 15,000. Just the power of 10. It's approximately 10 to the power of what? Okay. 10 to the power 6,517 kilograms. That's the starting mass of the rocket. So that's more than the mass of the universe. More than the mass of the universe. More than mass of universe. And mass of the universe is approximately, well, mass of the observable universe. We can't say observable. Observable universe is approximately 10 to the 73 kilograms, roughly. There you go. Okay, around 10 to the 70 kilograms. Yeah, so something. All right. Now, what do you need to change? Okay, so this rocket will not reach 1/10 of the speed of light, even if all the universe was turned into fuel. What can you do? What modification do you need to change? What do you need to change about the rocket in order to smaller rocket? Well, if you take a smaller rocket, that would be, let's say, a 1 kilogram rocket. It would be 1 times e to the power 15,000, which is 10 to the power 6,514. I don't think this will make a difference. Yes, expel gases faster, of course. The only way you need to expel gases faster, increase U, need to increase U, which is the speed of the gases. And one of the prototypes, well, one of the ideas is to power a rocket using photons. Photons travel at the speed of light. Example, power the rocket using photons with an incredibly high velocity. Then yeah, you can reach speeds, significant fractions of the speed of light, because then if you say example, if you travel at the speed of light, so mass, the initial mass is going to be 300 million meters a second multiplied by E. Oh, sorry. The initial mass is 1,000 multiplied by E. The speed of the 30. You're trying to reach 30. So using photons. 30 million divided by 300 million. That's going to be 1/10. So it's 1,000. E to the power 0.1. And so it's 1,000 multiplied by E to the power of 0.1. It's 1,105 kilograms. So the mass of fuel is 105 kilograms. So if you were able to expel the fuel at the speed of light, you would only need 105 kilograms of it. The only thing is, you can't take 105 kilograms of photons because photons are massless. That's a problem. Maybe you can solve it. Okay. One of the things. Another idea is to use a solar sail. That's another idea. So there's a question. Could you explain how to form the rocket equation again? So the rocket equation is a simple conservation of momentum. If you have a stationary rocket and it shoots gas one way, the rocket travels the other way. The momentum of the gas and the rocket is the same. So UdM has to be equal to mdv. The only problem is dm is negative because that's a decrease in the mass of the rocket. So we just put a minus, stick a minus in front, and that is the differential rocket equation. Does that make sense, Rakesh? Now, all you need to do is integrate the equation between the limits, and the limits are the starting and the final values of v, and starting and the final values of m. The rocket starts heavy and ends up small. It starts with 0 speed and ends up with speed vf. Okay. Another differential equation. A pollen particle of mass m is falling in the air and experiencing a drag force, where v is its velocity and b is a known constant. Find the velocity vt of the particle as a function of time. Okay, so we have a particle falling through the air. So obviously there's mg involved, and there's a drag force. The drag force is bv. Well, minus, it's in the opposite direction. That's why it's minus. First of all, what are the units? What? Okay, never mind. That's fine. So writing down, it's accelerating downwards, writing in Newton's second law. Newton's second law. Mass acceleration of the particle is equal to mg minus bv. And this is a differential equation. Question is, why is it a differential equation? Because, for example, y plus x equals 3, that's not a differential equation. Not a differential equation. The fact that the velocity is changing doesn't make it a differential equation. A differential equation that contains a derivative. Yes! Sanjbati. Apologies if I mispronounce it, because acceleration is the derivative of velocity, of course. A differential equation is an equation like this. Derivative of y plus x equals 3. That's a differential equation because it contains a derivative. We won't write v as a derivative of x, but a is a derivative of v. So m dv dt, because a is a derivative of, equals mg minus bv. All right. Now, what can we do? Let's divide. Should we divide by m? Will that make life easier? I'm not sure about it, but no, let's not divide by m. that won't make a difference. I'm going to treat this as a single term, and I'm going to divide by mg minus bv. This is called separation of variables, and then I'm going to multiply by dt. So I'm going to write m dv divided by mg minus bv equals dt. So what I have done, I've separated the variables. There are two variables, v and t, because m is a constant, g is a constant, b is a constant. So v is a variable and t is a variable. So I have one variable on the left and the one variable on the right. So it's separation of variables. Okay. So now I'm going to play a trick here. I'm going to take minus b out of the denominator. So it's m dv minus b v minus mg over b dt. And do I want to? Yeah, I want to put this here. I want to multiply everything by minus b. So I take away minus b, so minus b. Okay. Now I have m dv over v minus mg over b equals minus b dt. Now I can integrate it. So I actually do that. I integrate it. T changes from 0 to t, to where t is the final time. And velocity changes from 0, because initially it starts moving, to v. All right. So m. Who could help me with the integration of this bit? It's minus b. And what's the integral of dt? Ooh, logarithm of v minus mg over b between limits 0 and v. Well done. And minus b, that is just t. The integral of dt is t between limits 0 and t. So I substitute the limits. So m logarithm v minus mg over b minus logarithm 0 minus mg over b equals minus b t. Okay, so m logarithm. So v minus mg over b. What is mg over b? Well, at terminal velocity, bv equals mg. And that means v equals mg over b. And that is the terminal velocity, or maximum velocity. And that means that the modulus of v minus mg over b, because mg over b is the top velocity that is possible, v minus the maximum velocity is always going to be negative. So I'm going to replace the modulus with mg over b minus v, because v is always less than mg over b. So I'm changing the order. Minus logarithm, this is minus mg over b, so minus, it's a negative. Modulus of a negative value So it's going to be logarithm of just mg over b equals minus bt. So from here, I have m logarithm multiplied by logarithm mg over b minus v mg over b equals minus bt. What can I do here? I can multiply everything by b. So it's m logarithm mg minus bv over mg equals minus bt logarithm mg minus bv over mg equals minus bt over m, and mg minus bv over mg equals e to the power minus bt over m, 1 minus bv over mg equals e to the power minus bt over m. Bv over mg is equal to 1 minus e minus bt over m. So v is equal to mg over b, open bracket, 1 minus e minus bt over m. And that's the velocity. That's the function of the velocity. Let's sketch that. So y is equal to, we'll use something generic, mg over b. So I don't know, 20, open bracket, 1 minus e to the power minus 0.4 x. And of course, x is greater than 0. Just remind us of something like a skydiver reaching terminal velocity, or a pollen grain reaching terminal velocity. Oh, okay. So the top speed is mg over b, v max. And then you just slowly, well, slowly, and depending on coefficient b. So b is, if you have more friction, then this would be 0, or less friction, 0.1. So it'll take more time to reach. More time to reach. 0.4. Takes different time to reach top velocity, depending on the mass and the yeah. Oh, I went through that. You must have missed. So there's a question: why is the top speed? A top speed is mg over b, because at terminal velocity the forces have to be balanced. Forces balanced. So BV has to equal to mg. B is a coefficient, depends on the shape of the pollen, the radius of the pollen, and the density of air, the viscosity of air, the temperature of air. So yeah, all sorts of things. So B is just a constant. Okay. Right. And problem 7, how to do this. So this is a complicated diagram. So assuming that R1 is R2 and that's equal to R. So effectively that it means that this is R, this is R, this is 2R, and this is 2R. So there's no twos. Can I just white? Ah, yes. That makes sense. Find the current in each branch. So we're using Kirchhoff's laws. So this is physics, of course. So let's start labeling the currents. So the current through the battery, let's call it I0. And here it splits. I'm going to call this I1. This is I0. And well, this one I can call I0 minus I1. Yeah. Rather than introducing a new variable, I know that because the current splits, some of it goes here and some of it goes here, because the total current has to equal to I0. And indeed, I1 plus I0 minus I1 is going to be I0. So then I don't know which way the current will flow in this resistor. Actually, I do. So here we need to imagine, because look, if this resistor wasn't here, life would be full of sunshine and butterflies, right? Because there's nothing complicated about this question whatsoever. Do you agree? If that resistor wasn't there, everything would be perfectly fine. Actually, we don't really even need this. So let's do some calculation. So if the current in the top branch, because the total resistance of the top branch is 2R. So if you had for this circuit R and R, and you had 2R and 2R, that's EMF, and the current, sorry, it's the other way around. It doesn't really matter, but just for the sake of it, the current here. So the current here would be the voltage divided by 2R. So the current, the top current is EMF over 2R. And the current on the bottom is EMF over 4R. And here it's the total, it's EMF over 2R plus EMF over 3R. So it's 3 EMF over 4R. That's the total current. Now, let's say for the sake of it, this is 8 volts. If this was 8 volts, then the voltage on each resistor would be 4 volts. 4 volts and 4 volts. And this would be 4 volts and 4 volts. So now we need to think in terms of potential. So we can say that the potential here is 0 volts. 0 as in, yeah, the starting point. We can also earth, like in electrotechnic, they sometimes earth this end to say this is 0 volts because the ground is 0 volts. The battery increases the potential by 8 volts. So the potential here is 8 volts. The potential here is still 0 volts. And that means the potential here is 4 volts and the potential here is 4 volts. That means the potential difference between points A and B, potential difference between A and B is 0 volts. Yes, that means if you connect a resistor here, there will be no current through it. So it is as if it wasn't there. Yes, Karim, you're well done. Right. So there's no potential difference between A and B. Therefore, the resistor there won't be no current through the resistor. The resistor would make no difference whatsoever. Therefore, we've already found the currents. Resistor between A and B. B does not make any difference. Therefore, the current at the top is equal to EMF over 2R. Current at the bottom is EMF over 4R. And the current through the battery is 3 EMF over 4R is the total. And that's the answer. And I won't show this to you. So okay, so the top is 10, the bottom is 2R, so it's 20. This one is 20 as well. You see how the colors change because the colors actually indicate the resistance. There's a table of colors. I'm not an engineer, so I don't remember. But yeah. So yeah, look at the voltage on the battery. The voltage on the battery is 12. We already know that. So the voltage on this resistor is 6. So the voltage on this resistor is also 6. The voltage on this resistor is 6. So if you measure the voltage between these 2 points, you'd see that the voltage is 0. That means if we connect, even if you just connect a wire here, there's no current in the wire because the voltage is 0. So you can remove the wire, replace it with the resistor, and we have nothing will change. Still have 0 current and 0 voltage in this resistor. So adding a resistor does not change the current. Current is 0.6, and if we remove the resistor, it's still 0.6. And here the current is 0.3, twice, and this is 0.9. Okay. So that's quite cool. You're using the symmetry of the circuit to make predictions. So you ask yourself, what if the resistor wasn't there? What would happen? And this sometimes helps to know which way the current flows. If you, for example, here, well, we don't know the resistances, but imagine if we did, we could work out the voltage here and the voltage here, and that would tell us which way the current will flow. It wouldn't predict the voltages though, because the voltages, if the so the voltage across A and B, voltage across A and B can predict the direction of current right? But the VAB will change when a resistor is added. So let's say we have R1, R2, 2R1, 2R2. So this is 10. Let's make this 15. And this is 20 and oh, it's still 0. Actually, yeah, I didn't notice that. I didn't notice that they were the same. Yeah, it's the same. The answer would still be the same. It won't change because you still they're proportional. But okay, let's not make them proportional. Let's make them something else. Let's make this 20, and this will make 30. And so now you can. So this is the direction of current. And we can see that the voltage across A and B is negative. And current will always flow from high potential to low potential. So this is high potential and the bottom is low potential. So if I introduce a resistor in here, in between, the current will flow from bottom to the top because the potential at the bottom is higher. So this is high potential, low potential. And let's see if that is true. The current will flow upwards, and it did. Now, what if I just introduce a wire? It's the same thing. But also, please note that the voltage is 2.4. The moment I introduce a resistor, the voltage changes to 0.86 because I'm allowing current to flow. The voltage will change, of course. And what's the voltage going to be if I introduce a wire? What's the voltage going to be? Can somebody predict? What's the resistance of a wire? The resistance of a wire is 0. So the voltage is IR. So whatever the current is, the voltage across a wire will be 0. A wire eliminates potential difference. That's a very important one. Oh, these wires, we're assuming wires have no resistance. If a wire has no resistance, the voltage would be 0. And even in the extreme case, if we take a battery and we connect the wires, so we take a voltmeter. Oh, I can have 2 voltmeters. I didn't know that. So if the voltage is 9 volts, but if I short the battery, the voltage drops to 0 because the wires have no resistance. Yes, of course. You can also use that. Current takes the path of least resistance to see which way it will go. Absolutely. But sometimes you can't make a prediction. And in that case, all you need to do is just guess. If you can't predict the direction of the current, just guess. And then if it's positive, then your guess is correct. If your answer is negative, then it means the guess is wrong. Okay. All right, we'll stop here. And yeah, so yeah, actually, let me let me finish the question. I can't. So the answer here, the current in this section would be EMF divided by R1 plus R2. And in this section is going to be EMF divided by 2R1 plus 2R2. So current at the top is EMF over R1 plus R2. Current at the bottom is EMF over 2R1 plus 2R2. Current through the battery is the total of the two, so it's 3 EMF over 2R1 plus 2R2. And current through AB is 0. There's not going to be any current. All right. So yes, we'll finish here. So I'll see you. I probably won't be here next week. But watch out for the updates, please. But, I won't be here. I'm asking another person to do the webinar, David Vaccaro. So hopefully you'll have, fingers crossed, you'll have a webinar next week. Otherwise, I'll see you. Yeah. See you.